Our master plan for the semester is to talk about 4 programming paradigms, 2 of them at some length and the other 2 very briefly. We've been doing functional programming. We're done talking about that. It doesn't mean you're done using it, but we're done talking about it for the most part. We're going to be talking about object-oriented programming, which you've certainly heard of and have probably actually used in whatever school you were at before this one. I'd like you to try to forget that you've used object-oriented programming and really look at it with, beginner's mind, so that you can see maybe a different point of view about it from what you've seen before. Not that that other stuff is wrong, except where it is, but having more than one way of looking at it will help you understand the big picture. So the big picture is up here. This is an abstraction diagram, a little bit different from the ones you've seen before because of that dotted line partway down. The dotted line is an abstraction that takes place entirely in your mind. So there aren't any selectors or constructors associated with it. Above that dotted line is the central metaphor of object-oriented programming, which is that of multiple independent intelligent agents. So multiple, of course, means there's more than one, which is different from what's really going on inside the computer. Really, there's the one computer running your program. But we're trying not to think about that, and instead we build an abstraction in which every window in your window system is a separate entity. Every spaceship or gorilla or, Pac-Man in your game program is a separate entity, and so on. Independent means that each one has its own program. Some of them may be similar to other ones, and some of them may be completely different from other ones. But each one runs independently of the other, except that they have ways of interacting with one another. So it's just like, in this room there are a lot of people, and you can, go over and tap your neighbor on the shoulder, and by doing that, you are causing that other person to get a message that you want to have some kind of interaction. But most of the time, the person you're tapping on the shoulder does whatever he or she does completely separately from what you do. And just every once in a while, you interact. So that's multiple independent. Intelligent means, they know how to do stuff. So it's different from the data structures we've seen up to now. For the most part, the data is just data. It's like numbers or something. And the intelligence about how to do things is in something separate from the data, which is procedures. And here we're putting those together so that these agents have data-like aspects. They remember stuff, but also they know how to do things. So that's the metaphor. Now, in order to implement that metaphor, looking at it from a technical standpoint, there are 3 things we need. And that's what's right underneath the dotted line. The 3 things are message passing, which we talked about last week, local state, which we'll be seeing this week, and we're going to really understand better next week, and inheritance, which is the idea that some of those independent agents are a lot like other ones, and you don't want to have to program each one from scratch. Okay, you want to be able to use the behavior of one. You want to be able to say, this kind of thing is just like that kind of thing, except for the following differences. So if we have, let's say, a kind of object called a person, and there are many, many behaviors that all people share, like we talk and we walk and we eat and things like that. Then we can say, well, there's a class of professors who are people, and they do everything people can do, but they also lecture. And then there's a class of students who are just like every other people, except they have haircuts, you know. So that's inheritance, and we'll be talking about that. What we're doing this week, this is stuff that's not in the book. We are implementing on top of Scheme, a kind of Scheme++, an object-oriented system in Scheme, based on Scheme. We're doing that in order to make a connection between what we're going to do next week and what you've probably done before in classes, which isn't going to look much like next week's exploration of how to make object-oriented programming actually run in Scheme. So we're starting with something that sort of uses the vocabulary that object-oriented programming uses. And then next week, we're going to see how that's actually implemented, but I'll give you a hint. It's going to turn out that once you have Lambda, object-oriented programming is just a trivial application of Lambda. And I'm saying that because there's kind of a mystique about object-oriented programming that you have to have a special object-oriented language to do it in. And you'll see that that's not true. If you have a good programming language to begin with, adding object-oriented programming on top of it is no big deal. And that's good because you should understand how things work. Right? One of the goals of this course is when we show you about a programming paradigm, we don't just want you to see how it's used, we want you to also understand a little bit about how it might be implemented. Because that makes you a better and wiser practitioner later on. Okay. There are 4 components to our object-oriented language. They're define class, instantiate, ask, and usual. Ask and usual are like selectors. Define class is like a constructor, sort of. And instantiate is actually both. Because in this language, as in most but not all object-oriented languages, we have the idea of classes and instances. So person is a class. Brian is an instance of that class. Okay? So an instance is a particular one. The class is sort of the general description of the behavior of things like that. So define class creates a class. What instantiate does is it takes a class as argument and creates an instance of that class. So from the point of view of the class, instantiate looks like a selector. But from the point of view of the instance, it looks like a constructor. Got that? So who's with me on that? Sort of. I'm seeing some sideways thumbs. So, okay, if I wanted to model us in my computer program, I would start by saying define class person, blah, blah, blah. And then I would say define Brian to be instantiate person, blah, blah, blah. Okay? So instantiate looks at the person class and sort of pulls out from that the information to make an instance, which is Brian. Okay? So instantiate doesn't make a class. It's a selector for classes, kind of. But it's a constructor for instances. All right, so let's look at some examples. Maybe that'll make things clearer. The way define class works, it's a special form, which is to say it doesn't have the standard syntax of Scheme quite, and it doesn't have applicative order evaluation. And the pieces of a defined class are called clauses. And they're kind of like cond clauses. That's where we got the name. In that there's a bunch of them. But they're different from cond clauses, because cond clauses, you really only do one of them. And here we're going to actually use all of them. So actually, define class Oh, sorry, first things first. If you look at the highlighted text right here in the second half of the screen, you will see that in order to use define class, we have to first load this file from the library, obj.scum, in which these things, these four things, are defined. Okay? So that's the first thing I should have said. So now, define class, it's meant to remind you of how define looks when you're defining a procedure. So if this just said define instead of define class, we would be defining a procedure named complex, and it would have formal parameters, real part and imaginary part, right? And then all this other stuff would be its body. Okay, so that's how define for procedures works. And define class has much the same structure, even though it's doing a different job. So we are defining a class named complex. It represents complex numbers. And these things are called instantiation variables, which are like arguments to the class. I'm going to start writing things down here. So we have the names class, instance, and now I've talked about instantiation variables. Oh, and I used the word clause. So to show you how an instantiation variable works, let me jump right in and make an instance of this class. So I'm going to say define C1 instantiate complex 3, 4. So C1 now represents the value 3 plus 4i. If we actually look at what C1 is, it's a procedure. That's what we're going to be talking about next week, how we do this. But it's much like the message passing approach that we saw last week, where a datum takes the form of a dispatch procedure that you call with a message, and it does something or other.